Hello everyone, and thank you for tuning in. This is Ahmed Abdelwahab, and today I'll be presenting to you our work on covert channels in cyber-physical systems. First, I'll be giving a brief introduction about the topic and the motivation for this research. Second, I'll discuss the problem setup. Then I'll go ahead and talk about the proposed solution, both in terms of the covert channel design and the proposed implementation for the controller for this covert channel design. Finally, I'll end my presentation with simulation results and conclusion and future works. A covert channel is a type of attack that allows adversaries to transfer information between entities inside the system that, according to the defined security policy, are not supposed to communicate with each other. The covert channel problem has attracted a lot of attention in the cybersecurity community since the 1970s. But recently, some works focused on establishing covert channels between devices in networked cyber-physical systems. In our work, we present a covert channel between a compromised controller and the measurement channel in a cyber-physical system. In this design, we assume that there is no special hardware is required and that we do not need an additional explicit communication channels. Our objective in this case is to establish a covert channel to send a message vector from a sender inside an infected control logic to an eavesdropper on the covert channel. We consider the class of network control systems shown in the figure, where the system dynamics are described by the equations shown here. While dP and dm are bounded process and measurement noises, we assume the network controller consists of two modules: the control logic and the anomaly detector. The control logic is in charge of computing the control input UK, while the anomaly detector is a binary detector based on the expected one-step ahead evolution of the measurement vector YK. The attacker's aim is to establish a covert channel inside the system between a sender and a receiver. The sender in this case will be located inside the network controller that will try to infect the control logic, and the receiver would be on the measurement channel. The attacker's resources are a full model knowledge, as well as the ability to inject malware into the control logic, which is disruptive resources, and disclosure resources in terms of the attacker being able to read sensor measurement on the measurement channel. The attacker design problem can be formally stated as follows. Given the plant model, the anomaly detection rule, and the adversary model, we need to show the existence of a covert channel such that a binary vector message can be sequentially encoded in the control action UK coming from the infected control logic by the sender to the receiver on the measurement channel. The control action does not trigger the anomaly detector, warning the system administrators of detection rule violations. Finally, the encoded message can be correctly decoded without ambiguity on the receiver end on the measurement channel. The intuition of this covert channel design is based on the attacker's knowledge about the plant model and his ability to arbitrarily change the control logic. So considering a message vector M that consists of binary pieces of information equal to 0 or 1, the attacker replaces the legitimate control law with a switching logic, enabling him to encode the message on top of the input signal UK. If the bit of information being sent is equal to 0, the sender would send U0K to the plant, and if the bit of information equals to 1, U1K would be sent to the plant instead. This switching controller is known to both the sender and the receiver, the eavesdropper. So the eavesdropper, when he receives YK plus 1, it can be used to determine if U0K or U1K has been applied to the plant. hence successfully decoding the message. Based on the one-step output evolution prediction set, the receiver determines which control law has produced the given measurement. There are three possible cases. In case 1, yk plus 1 falls within the red set, which is y0 plus, which entails that the control action u0 has been used to produce this output, and a bit 0 is decoded. In the second case, a bit 1 is decoded because the received measurement yk plus 1 falls within the prediction set, the blue prediction set y1 plus. In the third case, the received measurement yk plus 1 falls in the intersection of the two sets. Therefore, it cannot be determined for sure which control input has been used. The sender is aware of the bit decoded by the receiver because they perform the same operations. Therefore, if case 3 arises, then the received bit is discarded and retransmitted again. To show the effectiveness of the proposed covert channel design, we show how an infected switching logic can be obtained when a dual-mode set-theoretic model predictive controller is used. First, in an offline phase, the smallest, robust, positively invariant region T0 and an associated stabilizing controller is determined. Then, the RPI region T0 is enlarged by computing a family of robust one-step controllable sets, Tj, such that if the measurement signal yk belongs to the outer set, there exists always a control input uk that drives the status of the system one set ahead inside the family of one-step controllable sets until it reaches T0. Then, in the online phase, the infected control action U0 and U1 can be computed by solving the following optimization problem, which cost function ensures that there is a maximum distance between the centers of the two prediction sets y0 plus 1 and y1 plus. A set of simulation runs were carried out to assess the achievable transmission rate by the covert channel. Each run iterates for 70 steps, starting from a random initial state in the outer set of a family of 100 controllable sets, and the obtained average probability of successful decoding was 72.5%. On average, the channel transmitted around 50 bits in 70 time steps. By considering a single run, we have these two figures. First, on the right, the output evolution of yk is depicted, and the robust one-step output reachable sets at k equals 49 and k equals 50 is also illustrated. At k equals 49, the measurement signal falls within the red prediction set, which is decoded as successfully as 0. And at y50, the measurement signal falls in the intersection between the two prediction sets, the blue and the red sets, which means that the bit is discarded, and the sender will attempt to send the bit again in the next step. On the left, we have the set membership index evolution, which is an indication of a normal or an abnormal system behavior. Here, despite the infected logic, the plant behavior is normal. In other words, the set membership index has a monotonically decreasing behavior regardless of the presence of an infected logic. In conclusion, we showed the possibility of establishing a covert channel in cyber-physical systems, which is capable of transmitting sensitive information from an infected network controller to an eavesdropper which has access to the feedback channel. The presented approach encodes the message in the control system's dynamics without creating any additional explicit communication channels or hardware. We used the dual-mode set-theoretic model predictive controller as an example to show how encoding-decoding scheme can be performed over such channels. Finally, we'd like to note that research related to covert channels in cyber-physical systems is still in its infancy, and different challenging problems remain to be explored in future work. For example, from an attacker's perspective, The design of an infected control logic to maximize the covert channel transmission rate and bandwidth is of interest. Also, in our work, we assume that a resourceful attacker. Future research can be directed towards establishing a covert channel with less resources available to the attacker. Also, from a defender point of view, the design of control architectures and detection algorithms capable of preventing or detecting covert channel is of interest. Thank you very much for listening.